We're going to be talking about inference for simple linear regression. So now that we've fit the models, we want to test our hypotheses about whether those models are an appropriate fit for the data or are useful for informing our understanding of the relationship between the two variables of interest. We need to back up a little bit and talk in a little bit more detail about the regression assumptions, both because we didn't cover that in the previous section, but also because they pretty directly sort of link into hypothesis testing. So the regression assumptions are listed here: linearity, independence, normality, equivariance, or what the book refers to as uniform spread, zero mean, and randomness. You could use the sort of pneumatic of LINE, linearity, independence, normality, and equivariance, and then I've added the randomness and zero mean at the end for line-ers, in case that is helpful for remembering which are the regression assumptions that we need to consider. So to work through each of those, some pieces that are useful, I think, is to differentiate which of these we can detect visually and which we can't. So independence, randomness, both are hard to tell visually. They really require us to know something additional about the data, either how they're collected, who's in the sample. Independence, for instance, tends to be violated by repeated measures on the same observation, having two people who are related to each other. Thus, they share some information, and knowing something about one tells you something about the other. Those sorts of violations. Randomness is also a function of really understanding the data in the sense of, is this appropriately selected sample for making the inferences to a larger population? So if we had taken a convenient sample of the first 10 people who walked into Burton, would that actually be in a given period of time, would that actually be an appropriate reflection of all Smith students? No, right? And so if we're going to use those data on the 10 people to refer back to the population, we want to know that that was a randomly selected sample such that we can have more certainty or understanding of how much a reflection our sample is of that population. Zero mean you can see visually, but we don't tend to talk about it much. It's mostly mathematically sort of set by how the line is fit. So then what we do focus on in terms of the visuals are linearity, normality, and equivariance. And so we have a couple of different plots that we've looked at already briefly, and you've done in the homework to think about this. So all of these can be assessed with the residual fitted plots to a certain degree. Normality is more clearly considered in histograms or the normal QQ plot. So I want to walk through first some examples visually where those assumptions are met, just to get a sense of what it looks like when these things are met, when it looks right, and then we'll go and give some examples of when those assumptions are violated, what you would be looking for, or examples, and in this case, pretty extreme examples of when those are violated, what it looks like, so that you can, when you are looking at something, be able to assess, does this look closer to what we would expect, the sort of ideal case, or the more extreme case of the violation? So, right, with any regression model, we're starting out, even before we fit that model, with a scatter plot. So looking at a scatter plot where we have these 5 criteria: direction, strength, the magnitude, unusual observations, and linearity. So linearity is already one of these, and we can evaluate those with a scatter plot initially. Then we can also, after we fit that regression model, think about linearity, normality, and equivariances in the residual fitted plot on the left, and thinking about the distribution of each of those sets of residuals at given points of fitted values on the x-axis. So what's going on in the left is something you're coming to see more frequently, this residual fitted plot where we have the fitted values on the x-axis and the residuals on the y. The plot on the right has a similar kind of idea where we've binned or sort of combined in 25 unit increments, the fitted values for each of um, the observations, and then the distributions are really illustrating this idea of equal variances more explicitly. So in either case, what we're looking for here in terms of equal variance is really a sense that there is kind of this constant, more or less constant, um, like almost sort of a band at theoretically even points. So at sort of positive 20 and negative 20, for the most part, that's where the variance is around, and that's pretty even across all of the range of these fitted values. You can see that here with these distributions, that they all look like a fairly similar shape, and numerically they have the same standard distribution, or I'm sorry, standard deviation, and that's the goal for equal variances. For normality, that takes these sort of distributions a step further and makes assumptions about whether it's not just that they're equal, but that uh, do they have a normal distribution in terms of comparing these distributions to the normal distribution, not necessarily a standard normal, but this idea of essentially the symmetric bell-shaped curve. And I would say in this case, all of those are pretty well met. Linearity, we're looking for in the residual fitted plot in the sense that, again, the kind of default assumption is linearity. So if we don't see violations of that here, like some persistent shape of a kind of curved line or something along those lines, we I think can pretty confidently say that linearity is met. Why equal variance becomes useful to be thinking about is that the notion of the distribution and how that has implications for statistical inference. So here we've taken this plot on the right and just sort of flipped it 90 degrees so that the residuals now are the x-axis and the fitted values are the y. And so what we're looking for here is that this black bar in the middle, this sort of thicker black bar, is the mean. The dashed bar is 1 plus or minus 1 standard deviation, and then the solid, sort of thinner black bar is plus or minus 2 standard deviations. And those become really important to consider when we're thinking about statistical tests that we make under a normal distribution. We'll talk about it in a minute. We make certain sets of assumptions about how the shape of a distribution is has a certain percentage of that distribution at certain points. So in other words, with a standard normal distribution, we would know that within plus or minus 1 standard deviation of the mean, we would have 2/3 of the data, and plus or minus 2 standard deviations of the mean, that we would have 95% of the distribution. And that's part of what helps us to understand and use these kinds of cut points for statistical tests and p-values, right? This 95% of the data being within 2 standard deviations helps us to know that when we have a test statistic that's much further out, the test statistic of 4, right? That's much further than 2 standard deviations. It's 4 standard deviations. So having equal variance here is really important, because if we had a much wider spread at some parts of the data, that the sense of where these cut points should be for statistical inference are going to be changing. They're going to be different at one part of the graph than they are at the other. But instead, what we want is, and our assumption is, that these are really equal. And that looks more or less true in this case, that it's not exactly equal across all of these. The variance is actually equal. The distribution is a little bit different. But this looks pretty good for us. So this is just to connect that idea of why we're thinking about equal variance and statistical inference, is that it really is this sense that what we want is the same shape of a distribution, such that the cut points that we're going to be using for inference are going to be the same across all values of the data. And we'll see this more clearly when we're looking at violations of this. Speaking of violations, here's an example of, in the scatter plot, before you would even fit a regression model, I think most people here would see that there's a pretty, it's not that strong of a curve, but there's a definite curved line here where a linear model really wouldn't make much sense. So just to illustrate that that's here's where the regression model for these data would be fit. And you see that violation of linearity in this residual fitted plot, right? We see that the points are not just randomly scattered above and below, that actually there's sort of a bunch of points that are missing in the middle above and many, many more that are below that are missing on the lower and the higher end, right? We see still this sort of like curved shape that's in the residual. That's a direct kind of correlation to if you just sort of rotate your head, right? You see the same kind of pattern of what's going on here is reflected here of the residual fitted plot. So this sense of what we're seeing in scatter plots pretty directly corresponds and is evident in residual fitted plots. The equal variance assumption that we were just talking about, the clearest and most explicit, although this is almost a sort of stereotype of the extreme example, is this fan shape, where as the values are increasing, that the residuals are getting further and further apart from each other. So this is a case where the model is doing a much better job at the lower sort of at one point, I should say, and much worse at another point. And you can see here that these distributions actually flatten out a lot more at the higher values of the fitted values and are really tight around this sort of smaller value because the distribution is much tighter than it is out here. And so that's, again, if we were to take that example that we were talking about before, where we're thinking about how this relates to statistical inference, if we took the average here, we would see the mean is 0. These are 1 and 2 standard deviations, the dashed and the solid line, as we saw before. One way to start to see this, right, is that if you look at this smaller, the sort of first bin, that's a really tight distribution where that wouldn't actually even hold true, that the dashed line is actually much further away from the mean than probably 1 standard deviation, and that for this last bar, that actually there's still a lot of the data that's beyond plus or minus 2 standard deviations from that mean. So we have these really different distributions, and if we decided that our cut point is this plus or minus 2 standard deviation should be that 95% of our data is within that, that's going to be not really true for many parts of the data, but potentially only true on average, in which case it'll give us the wrong answer, right? So if we, for this particular bar or the segment that's in the front, right, its distribution was really, really tight. That's here in the blue. And if we looked at this last group, the plus or minus 2 standard deviations here in the red is actually much, much wider, right? And so then this is saying that if you took any one of those groups, they'd give you really different answers, and that across the board, the average is like not actually, this average is not actually really a very good fit. So there are ways to deal with this equal variance violation, a number of them, but this is just to sort of highlight what the implications are there. So another thing to note here is that equal variance and linearity can both be violated at the same time. So this is an example on the left of a regression model of something that looks pretty curved. It's a little hard to tell since there aren't that many data points. But another piece of it is that there's much more spread in the data at these upper values than there are at the lower values, where they basically just sort of fall in a line, right? So we can see that linearity is not being met in this residual fitted plot for sure, because we see this curved pattern, but we also see this spread that's happening at one part of the distribution of the data that wasn't in another. So these aren't mutually exclusive, and in fact, they could happen at the same time. So how does that connect to hypothesis testing? Remember that we have our null and alternative hypotheses, and that these are specified before we fit the model, and that 0 is really corresponding to this horizontal line, right? So our null and alternative hypotheses, for the slope at least, for beta 1, are that our null is that beta 1 is 0, so that means it's flat, right? When we're thinking about rise over run, for every 1 unit increase in x, that y increases by 0 is a flat line, right? And so that's saying that there's no real relationship between the explanatory and the response variable. So some other kind of conceptual ways to think about these hypotheses is visually, right? We're seeing this red horizontal line, and what we're saying is, does fitting a model or the results of our model, which aren't shown here, but you can almost sort of visualize what that might be. Is that doing a better job of predicting y than just using the average value of y, which is this horizontal red line? So a line with a slope that may be downward sloping, is that doing a better job of predicting the values for y rather than just saying every car is going to have the same price? You could also think about, is the relationship between x and y significantly different, probably steeper, than just this flat line, right? So those are two different ways of thinking about with a question that has more of an association in mind. Is the relationship sort of steeper visually than just a horizontal line? And from a prediction perspective, you could think about, could we predict the value of a car's price just by saying, on average, everybody should be considering that the mean is going to be a good fit? In other words, that there's no added value of mileage as a way to predict the price of the car. We should just assume that the car has, any given car, independent of its mileage, is going to have the same price. So our test statistic, if you remember from intro stats, this sort of equation for a t-test, where we had the mean minus or x bar minus mu, the sample mean minus the population mean, divided by the standard error. And in English, that's essentially just our estimate minus the null divided by the standard error. And since our null here is 0, our t-test, or our test statistic for a regression slope, is this beta estimate over the standard error of that beta estimate. I'm not going to talk a ton about what the standard error, how that's derived or what that is, but if you want to know, we can certainly talk more about it, and in fact, it'll come up a little bit more later this week. So once you do that test statistic, so R is going to give you out the beta value and the standard error. What do we do with it? So essentially, we use it to calculate this test statistic and then evaluate that on a t-distribution. So an example is given here for 28 degrees of freedom, which is how many degrees of freedom there are left from a simple linear regression model of these Accord data that had 30 cars in it. And you can use that test statistic to say, if you had a test statistic of 3, you're far enough away from the mean that you would suggest that we would be able to reject that null hypothesis. In other words, you want to be far out into this distribution because the amount of space, or the amount of data that's being kind of shown here in this blue section, that is at that point or further away, is directly corresponding to that p-value. So in other words, right here, there's 5% of the data that are in these blue segments, and these are asymptotic in the sense that the lines never quite cross the axis, so it just sort of goes on forever. So what we would want to say, what we're looking for is a p-value of that's less than 0.05, we would want to be at some test statistic that's at this point, which is here it's 2.07 or negative 2.07, or further away, to be able to say that we have the probability that we found this due to chance is less than 0.05. We need to be further into this distribution at this point or further out, right? So we want a big t statistic in order to have a small p-value. And you can use this link to go kind of play around with this as a test. I think it can be a helpful one. The relationship here between the test statistic p-value and the hypotheses, you can think about this sort of like at least the US legal system, where everyone is assumed not guilty, right? The goal, or the burden of proof, so to speak, is to prove that someone is guilty. But you can never prove that someone is innocent. So this is just a note of caution here to remember that you can never accept the null hypothesis. You can only fail to reject it. So with the court example, someone is not guilty. You can't prove that they're innocent. You can only say that you don't have enough evidence to say that they're guilty. And so you render them continuing to be not guilty. Similarly, we can reject the null hypothesis and accept the alternative, right? We could say that someone is guilty because we feel we have enough evidence to say that. But we have to fail to reject the null hypothesis. We can't accept that beta 1 equals 0. We don't necessarily have evidence to say that someone's innocent. We only have evidence to say we can't tell that you're guilty. So we're going to say that you're not guilty, right? We can fail to reject that null hypothesis, but we can't accept it directly. So a couple notes of caution here. I'd be careful with the phrasing or their interpretation of a p-value. Often students will say, because the p-value is small, which is, I think it's leaving out a couple of key pieces of information of what exactly is small, what's your critical value, were you considering a p-value of 0.05 to be statistically significant, and for that matter, what does really small mean? You might just want to include the actual value itself. I'd also be careful with the implications of what a p-value is. People feel really drawn to the evidence of it either is or it isn't, right? It's a black and white, it's a binary. You either are p less than 0.05 or you aren't. But it's a much more nuanced and complicated argument to make than that, because what if you had something that's just over that line of 0.050001, right? How is that really that different? And so it also avoids the issue of clinical significance or a sort of substantial significance. So in other words, you could have something that's statistically significant, but it doesn't necessarily carry a lot of weight, right? The magnitude of the relationship is not actually very meaningful. It could be so small, and you could have so much data that you'd find a statistically significant difference. But if meaningfully, that small of a difference doesn't make much of a difference to the people who you're talking to, your audience, then it's important to be really cautious about statistical significance really leading the way. There's some readings here that I'd really encourage you to consider in terms of p-values, particularly in the second edition of the Stat 2 textbook. Confidence intervals help avoid some of that, the kind of binary nature of the p-value, because they express how wide the confidence is around that beta estimate being a reflection of the true population estimate. And that width of the confidence interval can potentially include that null value. And you might be able to show it's just barely including the null, and we think that maybe there's more noise in the data. It helps to articulate some of that nuance into the argument. So that's a look at statistical assumptions of regression and starting to get into inference. And then we'll talk more about unpacking some of that in the next class.